Well, thank you all for coming. I'm Karen Ferdin from Berks Gas Truth, and I've been working with the Lehigh Valley Sierra Club and the Pennsylvania State Sierra Club to put on this event today and last evening. So thank you all for coming out. It's great to see such a huge crowd. With no further ado, I will introduce Thomas Au from the Sierra Club Pennsylvania chapter, and he's going to introduce our keynote. So please give Tom a warm welcome.
I want to thank Karen and our colleagues for organizing this wonderful event. My name is Thomas Au. I'm the State Conservation Chair for Pennsylvania Sierra Club. And we've been working on Marcellus gas issues for about 3 or 4 years now. I want to introduce our distinguished speaker, Dr. Anthony Ingraffea. Dr. Ingraffea is the Dwight C. Baum Professor of Engineering at the School of Civil and Environmental Engineering at Cornell University. Dr. Ingraffea's research concentrates on computer simulation and physical testing of complex fracturing. He and his students have authored over 200 papers on this subject. He has twice won the National Research Council's U.S. National Committee for Rock Mechanics Award for Research in Rock Mechanics in 1978 and 1991. Why this is relevant to today's discussion is that extracting gas from Marcellus Shale and other shale formations involves hydrofracking, that is injecting water, sand, and chemicals under high pressure into the shale formation to crack the rock. So that's rock mechanics. Dr. Ingraffea explained to us in layman terms how this creates environmental problems. Dr. Ingraffea is well known within the environmental community as a scientist who provides us with the straight scoop. And with that, I welcome Dr. Ingraffea.
Good morning, and thank you. And thank you all for sacrificing what's going to be a big part of a beautiful day. The fact that you're here on such a beautiful day is an attestation of your seriousness about the issues that we're going to be discussing and working on today. So I really appreciate that, and thank you all for being here. I'll try to make it worth your while this morning. I also want to thank the sponsors and everybody who organized this thing and got me down here for this event. I usually start off by setting up some ground rules. I've been a professor for longer than you want to know, and so at the beginning of every semester there's always a set of ground rules, what I expect from the students, what the students should expect from me. So what you should expect from me is honesty, clarity, accuracy, and if you at any point figure out that I'm not being accurate or clear or transparent, make a note, and you have been given note cards to write down questions or comments. All of my slides will have numbers on them, so you can refer back to the slide by number so that during the Q&A we can go back and address the particular problem that you pointed out. What do I expect from you? Well, I can't expect you to take an exam sometime today, although I'd like to, really would like to, especially when we get to the calculus part. How many people here have taken calculus? You're kidding. There will be an exam. Love it. No, what I expect from you is a sense of curiosity, a commitment to think deeply about the things we're going to talk about today, and certainly a sense of humor, which you've already exhibited. And we'll test that sense of humor as we go on here. But I'll start by pointing out that I'm coming home again. I guess some of you have heard that I was born and raised at Easton. Nice place. And I could probably fill this auditorium with all my relatives. But you probably wouldn't want to meet a lot of them. Except for the two guys up there, so, okay. Anyway, so just to point out that I did spend some time not too far away, like about a mile down the road. Graduation 1965. Boy, that guy has come a long way. And you think I'm just doing that to, be nice and make you feel good about me. But Sister Marie Amelia was my calculus teacher. And since most of you took calculus, you're going to get this joke. So she taught me how to differentiate. Good. You're good. I can tell you right now you're good. And among the things she told me to differentiate between is fact and fiction, myth and reality. And that's the topic of today. And I realize that in the audience there are people who are just coming to this issue anew. You don't know much about the basics of the geology, the technology, the science, and the engineering of producing gas from an unconventional source like shale. On the other hand, there are people in this audience that know it better than I do. And there are a variety of learning styles that I always confront when I'm giving a lecture. So it's always a challenge for me to frame what I want to talk about in a way that most people can grab a hold of. And the framework I've been using recently is this idea of myth and reality. So the gas industry tells us things in various ways, through our legislature, through our regulators, through television ads, through blogs, through direct attacks. They try to tell us things. And the point I want to make here is that what they tell us always has a kernel of truth, as does a myth. A myth always has a kernel of truth. Otherwise, you wouldn't even think about enjoying reading about it or hearing it. Right? Think of all the myths that are in our lives. Easter, Christmas, whatever. There's always a kernel of truth. And then that kernel of truth gets embellished. And pretty soon it becomes mostly myth and not much truth. So I'm going to pick 4 myth truths, and we're going to delve into them. So here are the 4. Maybe we won't have time this morning. I'll get a sense of things as we go along. Maybe we'll only do 2 or 3. But each of these statements, as they're written, is true. Read them. Anybody from the gas industry here present today? Be truthful. I'm truthful. If you're here, let me know, because I want to make sure I'm addressing you too. Oh, you're kidding. Good. Okay, so those are true statements as they're written. And we're going to dive into each one and find out how much truth, and then how each of those true statements has been embellished, so that, in my opinion, it is now largely mythical rather than largely truthful. So the first one, if you remember back in 2006, 2007, 2008, when the industry rode into Pennsylvania, and the first thing they said is, don't worry, we've done this 1,000,000 times before. Fracking has been around since the late 1940s. We know what the hell we're doing. Okay, so let's take a look at that. But what they didn't tell you was that the kind of fracking that's necessary to develop an unconventional resource like shale had never been done in the state of Pennsylvania, except for 1 time or 2 times back in 2004, 2005 as an experiment. But they came in and said, we've done it before, what's to worry about? So the first thing we have to do is make sure everybody understands the basics. And remember, there are people in the audience who need the basics. Why is shale gas development called by the industry unconventional? Why was it new to Pennsylvania in 2007? And the reason is, from a geological point of view, is because the gas resource, in this case a shale, is highly impermeable and has low porosity. That's the classical definition of an unconventional resource from the industry point of view. From the practical point of view of regulation, legislation, and human impact, it's unconventional because it involves 4 relatively new technologies, all of which had to come together. This is how technology works. Somebody invents something that inspires somebody else to invent something that works with that invention, and pretty soon civilization advances, or in this case. So I want to speak briefly about these 4 technologies, when they came into existence, what they do, and how they are absolutely necessary of themselves, and how they're absolutely necessary in combination to make unconventional gas development from shale technically possible and economically, formally viable. I said formally, not formally, formerly, F-O-R-M-E-R-L-Y. It's no longer economically viable, but we'll talk about that maybe later. So, directional drilling. The way I'm going to talk about these 4 technologies is by way of cartoons, photographs, and videos. So be prepared. So directional drilling. What is directional drilling? Why is it needed? Cartoon. Most of you have seen this before. The typical cartoon of a pad on the surface, a drilling rig set up, and under ordinary circumstances, that drill rig would drill mostly vertically down into, for lack of a better phrase, a pocket of natural gas in a conventional source. And if you hit that pocket, you get gas. If you don't, you get a dry hole. But geologically, things are different for shale, because the shale might be 5,000 feet more or down, but it's only in a layer of 100 feet or so thick. And so if you just drill vertically down into it, your well is only going to be exposed to perhaps 100 or 200 feet of shale, and that's just not enough to make the well economically viable, even if you do hydraulic fracturing. The conventional hydraulic fracturing, low volume hydraulic fracturing. So the first and most important technology that had to come along was the ability to drill not only vertically, but in any direction you want, including horizontally or subhorizontally. In other words, have the well follow the shale. This is the first instance of humans obeying nature in developing a shale resource, because basically speaking, nature's in charge. So nature says the shale is thin and mostly horizontal or subhorizontal, so let's make sure we can drill so that we can expose what's called the lateral part of the well to as much of the shale as we want. And typically in Pennsylvania now, the most modern shale gas wells, the lateral is at least as long as the vertical, and in some instances much longer than the vertical. And the longest laterals I'm aware of are over 10,000 feet long. So you can drill down a mile and out 2 miles if you want to. So that's necessary. That's the first technology. Second technology immediately ensues from the first one. Because they can now have a long lateral, they're going to need a lot more frac volume. The fluid used to fracture the rock has to be of much higher volume. Well, why is that? Geology 101. We have a number of beautiful gorges around Ithaca, New York. You can walk up the gorges and see all these rock layers exposed. So if I'm walking up one of the gorges by my house, I can see a black shale that's exposed. This is a black shale. And all these nearly perfectly straight, and in this case almost perfectly orthogonal lines, who sawed them in there? How'd they get there? Anybody know? No? Good guess. Natural response to forces in the earth, and the force in this case was hydraulic fracturing. Shale is already naturally hydraulically fractured by gas pressure. Hydraulic just means fluid. Hydraulic fracture means fracturing by fluid. A gas is a fluid. And so many black shales contain high quantities of gas over the last 330 million years. And when that gas pressure got sufficiently high, the gas pressure itself caused those fractures to occur. So now if we have a long lateral depicted by this red line, imagine that lateral is thousands of feet long, what's the idea behind hydraulically fracturing shale? The idea is to refracture it, open up the existing fractures, and connect them to the well. Pretty cool. Basic idea. Connect a network of existing fractures in which large quantities of gas have already been stored. How do we know that? Because the fractures were created by gas. Right? That fracture system is a reservoir of natural gas. It's the primary reservoir. Not the only reservoir, but the primary reservoir of natural gas in a shale formation. So the idea, basic idea from an engineering technology point of view, is drill a lateral, intersect that lateral with as many of these natural fractures as possible. That tells us which direction to drill the lateral, because geology can tell us the direction of those natural fractures called joint sets, for those of you who are geologists. And now all we got to do is open a pathway between those fractures and this lateral, and that's done by perforating, which we'll talk about later. And you create a network, a flow network. So all these yellow lines are indicating that there's a gas molecule here. It can flow along that fracture back to a well. If it's over here, it can flow along this fracture, take a right turn or a left turn, get back to the well. That's called a flow network. The whole idea of hydraulic fracturing for shale formations is to refracture, reopen an existing joint set to create a flow network back to the well. Easily said, very difficult to do. Okay, well, the lateral can be thousands of feet long. The joint spacing is on the order of a foot or two, which means your lateral is going to be intersecting thousands of natural fractures, each of which has to be forced open with hydraulic pressure, water, chemicals, sand, proppant injected so that when the hydraulic fracturing process is over, natural earth forces don't close the fractures back up. The sand or ceramic beads prop them open. You're getting the idea here, right? But now it takes a lot of fluid. Typically, a conventional hydraulic fracturing job might take tens of thousands of gallons of fracturing fluid. In a shale gas well, millions. Not a factor of 10, a factor of 100 more. And as we'll see during the rest of my talk, that implies lots of scaling up of the logistics and lots of scaling up of the risk factors. So second technology, because you can drill laterally, you're now going to need higher frac fluid volumes, which creates another problem. Whereas you only had to inject a few tens of thousands of gallons at relatively low pressure in a conventional well to frac it, to frac an unconventional well, you have to pump millions of gallons of fluid a couple of miles through a pipe called a casing, which is of what diameter? Scale. Let's get scale right here. No, not 36 inches. Production casing, 6 inches or less, yeah. So I usually ask how many volunteer firemen are in the audience? Anybody? Okay. How much pressure does it take to get water to flow through a fire hose so you get enough pressure at the end to do any work? A lot, okay. So if your water hose, in this case, is a steel pipe that's a couple miles long and only 6 inches diameter, and you want to pump 5 million gallons of fluid into it at, say, 10,000 pounds per square inch in an hour, you need a hell of a lot of horsepower. And even then, you're losing a lot of that horsepower energy through frictional dissipation of the fluid flowing through the pipe, okay? Because even water dissipates friction. So you add a friction reducer. This is where the chemistry comes in. Slick water, or some other formula that makes the fluid that you're using for a hydraulic fracturing medium slick enough so that you don't need as much pressure in this. So you can actually get, at the end of that pipeline down there, enough pressure to fracture the rock. So that's the next thing. The chemistry of the fracking fluid had to be reinvented, and it's continuously being modified, reinvented, new chemicals are being tried. And last, but certainly not least, to make this whole thing even more economically viable, or now economically not very viable, is the use of multi-well pads and clustered pad arrangements. So let me tell you what I mean by that. So everybody put on our 3D glasses and imagine we're in a 3D movie theater, this time brought to you by Shell. And so this is an image from a 3D stereo movie that Shell has put together to try to explain multi-well clustered pads. So let me explain what you're looking at. This gray blob down here is the Marcellus Shale under an area of Tioga County, Pennsylvania. So how do they know that that's what it looks like? Good. Microseismic investigations, they can literally image what the Marcellus Shale looks like to some resolution. Here's a big fault that's running right through it. This is the surface, right, with topographic lines on it. And each of these verticals is the vertical part of a well. And each of these other things is the lateral part of a well. So you'll notice that this vertical starts out looking like a single line, but by the time it gets to the bottom, there's actually 6. So on that particular pad, there are 6 wells. That's called a multi-well pad. That's different from conventional gas development, where you typically have one well on one pad. All right, so there are pros and cons to this that we'll talk about later. But if you move over, say, a kilometer, there's another pad, and this one has 5 wells so far. This one has only 1 right now, but you can see there's a development trend here. So the idea here is if you're going to get gas out of a shale formation where the gas is virtually everywhere, you drill everywhere. Let me repeat that. It's a fundamentally important point in shale gas development. Once you find that you've got a region of shale gas which has a lot of gas in it everywhere, you drill everywhere. Otherwise, you're leaving some of your material in the warehouse, right? If you're running a business and your material isn't out in the sales floor, it's back in the warehouse, you can't sell it. So get to it, and the best way to get to it is by having closely clustered pads, perhaps a kilometer in every direction, and on each pad you drill as many wells with as long a lateral as you think is economically viable given the local geology and how much capital you have to spend. So ideally, and I'll show you another picture of how Shell is developing Tioga County, you would have a pattern like this that just keeps repeating. And to show you how that works in reality, I'm taking us to Texas, to the Barnett Shale play. And this is a Google Earth image of the Dallas-Fort Worth Airport. Runways, terminals, aprons. And now I'm going to flick the switch. And this is what that looks like to Chesapeake, the gas company. So Chesapeake arranged with the cities of Dallas-Fort Worth to lease the entire Dallas-Fort Worth Airport property. So you had one company dealing with one landowner, and they made nice. Okay? And when you make nice, the companies get to do exactly what they would do if they could make nice everywhere, which is to drill everywhere. So every one of those red dots is a pad, and every one of those red lines is a lateral. That's complete coverage. How much of the gas stored in the Barnett Shale under the Dallas-Fort Worth Airport has Chesapeake gotten access to? Almost all of it. Okay? That's the ideal. If the companies could get landowners to agree that they would only ever deal with one company, right? No competition between companies, and all the landowners agree to work with one company, that's what Pennsylvania would look like, or regions of Pennsylvania. And if you don't believe me, I'll show you a map later on of what Tioga County is looking like right now. So that's the ideal. So let's put it all together. Those are the 4 technologies that have evolved. How long did it take to get all these technologies to work together? How old, going back to this myth, they've been fracking for 60 years, so what? Okay. What's really new here? And how long did it take for all these technologies to come together? Well, here's the table out of the New York State Generic Environmental Impact Statement published late last year. The first horizontal well was drilled in the Barnett Shale in 1991. Slick water fracturing fluids were invented in 1996. Multi-stage slick water fracturing of horizontal wells, 2002, and the use of multi-well pads and cluster drilling, 2007. How old is this technology? Roughly 5 years old. Should it make you feel comfortable that mythologically you think it's being done since 1947? No, it hasn't been done. One part of it, fracking, has been done since 1947, but the scale of fracking is now almost 100 times greater. And so you're really dealing with an entirely new technology. And so Pennsylvania says, come on in. All 68 companies that got permits in 2007 were told, drill, baby, drill. We have regulations, except the regulations didn't apply to this kind of unconventional gas drilling. Okay. And so since then, how many times has Article 78 been amended? What percentage of Article 78 has had to be rewritten because you weren't ready? Regulatorily, you were not ready. All right, so there's the myth. Fracking for gas development is a 60-year-old well-proven technology. It's true. Fracking has been around since the late 1940s. The truth is that unconventional development of gas from shales, which is really what we're talking about today, which is why I object to this whole thing of being called fracking. It's so bothersome to me because it puts people's attention down there for 1 hour on one element of an entire process that I just tried to describe. So unconventional development of gas using high-volume fracking from long laterals is not a 60-year-old well-proven technology. It's still under development. Ask any of the companies right now how much research they're supporting and how to figure out how to do this better. There's a lot of research being done by academic institutions, including some higher institutions of higher learning in Pennsylvania, where industry is going in and supporting that research by millions of dollars to try to figure out how to make it work better. It's not standard operating procedure yet. So what? Why is this an issue? Why is it important that this is a relatively new technology? I already mentioned one. You weren't ready. Your regulations weren't ready. Your regulators weren't ready. You didn't have proper waste disposal facilities in place. I can go on from there, but the bottom line is there has been insufficient time to figure out what the impacts of all this are going to be, or even what they have been. Simple things that should have been foreseen in 2007. Gee, let's develop a database at DEP to figure out where the wells are being drilled. They don't get it right yet. Let's develop a database at DEP to figure out where all the waste is going. Still don't get that right. Let's develop a database at DEP to figure out how many violations are occurring, of what type, by which company, in which region. It took 4 years to get that database up for the public to see. And then we go on to higher order things like, okay, what's the long-term health impact in a region like the state of Pennsylvania of 100,000 unconventional shale gas wells in the Marcellus alone? Do you want to make a prediction now of what things are going to be like health-wise 10 years from now, 20 years now, 20 years from now, 30 years from now? Those studies should have already been funded and underway. Okay. Second myth with a kernel of truth. Fluid migration from faulty wells is a rare phenomenon. It's true. It's rare. What's your definition of rare? 2%?
1 in 1,000.
1 in 1,000? Let's find out. Okay, so what does methane or other hydrocarbon migration from a faulty well look like? Whoops. If I can find my glasses, here we go. I don't have any sound turned on here, but what you're looking at, oh, thank you. Wondered where those went. You're looking at a wellhead. This is the part of the well that's coming out of the ground, and inside of that is the production casing. The gas is supposed to be coming up inside that only. And this bubbling water is in the so-called cellar of the well. That's an area that's been excavated out around the wellhead, which frequently fills with rainwater or snowmelt. And that water now becomes a telltale. So what you're seeing is gas migration outside the well. So if gas migrates outside the well, it's possible that on its way up, it comes in contact with an underground source of drinking water. In other words, methane contamination of somebody's private water well. Even if it doesn't, it's now migrating directly into the atmosphere where it becomes a very potent greenhouse gas. Okay. So that's an example of methane migration from a faulty well. I'll point out some statistics later on about how frequently that happens in your state. I'll show you another example of methane migration. I'm a trout fisherman, so this one is especially egregious to me. Nice trout stream. And some fishermen were on it last June, and they noticed something they'd never seen before. So you saw Gasland last night? Remember the guys lighting the bubbling streams? So this has happened in a number of streams and in the Susquehanna River in Pennsylvania. So Chesapeake was fined $700,000 for some of these egregious acts to trout streams. And they voluntarily donated $200,000 to your plugging campaign. But that's irrelevant. The relevant thing is that the nearest gas well to this stream was 3,600 feet away. So your current regulations, if I'm correct, still say that companies have to be responsible, bear primary responsibility for methane contamination of an underground source of drinking water within 1,000 feet of their well. But here's prima facie evidence that migration can occur over much longer distances than much longer distances than 1,000 feet. In fact, geology says how far it can go. A regulation doesn't tell geology what to do, and a company can't regulate nature. Whatever nature says the gas can do, the gas can do. And if it's 3,600 feet or 5,000 feet, so be it. Write your regulations accordingly. Another thing to note here is that in one case, the previous video, you saw gas just bubbling up outside the well, very close to the well. Here you're seeing gas bubbling up 3,600 feet away. Can gas bubble up any place in between? Have you ever seen a forest floor bubble? Is the gas only going to bubble up in streams and rivers? Or only going to bubble up in cellars? It's going to come up wherever it wants to. And how will you know it's there? Can you smell it? You know, is somebody out there with a sniffer trying to find it? So do we really know how much methane migration is occurring even on wells where there's no bubbling in the cellar? No, we don't know. Not without regional measurements of flux, like that was just published in Colorado. Those of you who read the literature know that just about a month ago, a paper came out of NOAA and University of Colorado where they went over a long period of time, over a year, and set up measurement instrumentation to find out how much methane and other VOCs were in the atmosphere in Weld County. And they found out a hell of a lot of it, much more than we ever expected. Have those regional types of measurements been done in Pennsylvania in the last 4 years? No. Are they now going to be mandatory? No. So we'll talk about that later. All right, so why do wells fail? I want to get to that question about rare. To get the answer to the question about rare, you have to understand the various mechanisms by which wells can fail, lose their integrity, and allow methane or other hydrocarbons to migrate outside the well, where you lose control of it. Nature takes over at that point. So I did some experiments with Schlumberger. Yes, I did lots of research with Schlumberger for many years. We did some research back in the late 1980s. 1989, here's a 2-meter cube of tight sandstone, not shale. And we wanted to see what fracturing looked like. What do perforations look like? What does casing look like? What does cement look like? What does it look like? All the stuff you've been reading about. So you can't go down and look. But you can do a model experiment on real rock in a laboratory, which is what we did. So we drilled this block using a regular drill bit, and we put a casing in it, and we cemented the casing. We perforated the casing. We put red dye in the fracturing fluid, injected the fracturing fluid through the perforations, created hydraulic fractures, and when we were done, we broke open the block to see what happened. It's called a validation experiment. You have an engineering concept put into a computer model that says, here's what's likely to happen. But it's just a computer model based on people's concepts of what should happen. You have to validate it by doing an experiment to see whether your computer model is right. So I'm going to break open this block, and here's what you see. And here's your education on what's downhole. And this is the beginning of your understanding of all the things that can go wrong. What's silver is the casing. What's gray is the cement sheath, sometimes called concrete. It's not. It's cement. We've got a lot of that stuff around here, right? It's cement powder, water, and a few additives. So in this case, we broke open a block. These are the records of hydraulic fractures. They've been stained red by the stain, the dye that we put in hydraulic fracturing fluid. Here's another view. In this experiment, the cement remained intact. That hole is a perforation, shot with a perforating gun. Here's another one that's actually, you can see the tip of it in the rock itself. And again, a whole set of interacting, multiple, non-planar, realistic hydraulic fractures. So what can go wrong? Well, the casing could fail. There are cases of that in Pennsylvania. The cement could fail or not even be there. Lots of things can go wrong. So one way to look at those is to go to the industry itself and ask them to tell us what can go wrong. And so Southwestern Energy is usually held up as the model company to work with. I thought that was funny. But anyway, never mind. It's okay. There are a lot of, I'm from New York. We have a lot of these kind of crazy jokes about, shale gas development. What do regulations do? Regulations allow them to break into your house, but forbid them to scratch your furniture. Okay. And certain companies are held up as models of transparency and honesty and openness, and to a degree they are. So Southwestern, among all the companies, in my opinion, is the most transparent and honest. But what's your measure of honesty? So this is their video. This is a Southwestern Energy video that they put together. The red dots are gas molecules, right? And this is a well that's working perfectly. All the gas is going up the production casing. Here's gray. Remember, what's gray now? Gray is cement, right? White is no cement. In some places, you don't have to cement all the way to the surface. Every annulus, an annulus is the volume between the outside of the casing and the inside of the rock. And here are intermediate production zones, or shallow producing zones, aka the Dimick problem. The gas is not just all the way down there in the Marcellus, the gas is in intermediate levels of shale. And you got to make sure that the high pressure gas in these intermediate levels don't get outside the casing and up to the surface or into an underground source of drinking water. So this video shows everything's fine, the cement is intact, these molecules can't get through the cement, they can't get into the open annulus, therefore they can't get to the surface and cause bubbling, they can't get into the rock above and cause underground contamination. But there are many things that could go wrong, and I don't have time to tell you about all those things, so I'll just show you a couple of them and then show you the one that they didn't show you, which is the most important one, of course. So one of the things that can happen, for those of you who know about cement, and everybody around here knows about cement, the cement goes down as a liquid, right? All right, so they pump the cement down the inside of the casing, it comes all the way to the end and then goes all the way back up and it goes to a level called top of cement and then it starts to harden. Except before it hardens, it's a liquid. And if it's in contact with a high pressure gas, what happens when you squirt a high pressure gas on liquid cement? Well, you get a mess. And you get what's called channeling. So you can get loss of contact between the cement and the rock, and now the cement is useless. It's really not there. It's not doing its primary job, which is sealing the annulus. That happens a lot. That's one thing that can go wrong. Another thing that can go wrong is you get a leak through the casing. The casing is not one long continuous pipe, it's jointed. Every joint is a weakness. And every once in a while, the casing is produced faultily, and it contains cracks, or it can crack because it can get overpressurized. And if the casing fails, then you can get gas coming out and going to the surface, where it can either go into the atmosphere or build up pressure and go into an underground source of drinking water. You can have a poorly designed well, which is what happened in Dimick and most of the wells. They never got the cement to the top that they wanted to, so they had pressurized gas from shale formations above the Marcellus getting into an open annulus and going up to the surface. So again, there's a lot of cement knowledge in the Lehigh Valley, right? How long does it take cement to cure? How long does it take to go from liquid to solid? Well, no, I don't mean strength. I mean, when it goes from liquid to solid, a few hours, right? Depending upon the additives. You can delay it, you can accelerate it, depends upon temperature, all kinds of things. But what happens is that some engineer has to make a judgment. The cement engineer has to make a judgment, because if the cement takes too long to cure, they have to shut down the whole operation while they're cementing. Nobody else can do anything. And it takes many, many dollars per minute to be developing a gas well. So they don't want the cement to take too long to cure. What happens if the cement solidifies before it comes all the way back up? That's called lockup. Uh-oh, the cement didn't get to where you wanted it to go. And that's what happens again frequently. So instead of the cement top being up here and then forming hopefully a good barrier so that these molecules can't get into that open annulus, you have an open annulus totally open to gas pressure, and now the gas goes wherever Mother Nature says it can go. Now, the most common problem here is not shown. And it doesn't, I want to make sure you understand this, because there are millions of dollars being spent by the oil and gas industry on television ads and on newspaper ads right now that want you to believe that 4 layers of steel and 4 layers of cement are better than 3 layers of steel and 3 layers of cement. And 3 layers of steel and 3 layers of cement are better than 2 layers of steel and 2 layers of cement. And they want you to know that they're now using up to 4 or 5 or 6 layers of steel and cement. Doesn't make a damn bit of difference. There's always an outermost layer. There's always an outermost layer. I don't care how many you have, there's always a contact layer between the cement and the rock. And that's the contact, that bond. They can't detect it, they can't measure it, they can't observe it. There are techniques for figuring out whether the cement is in contact with the casing, with the steel casing. Lots of good technology to tell them that. But what they can't tell is whether there's good bond between the outside of the cement and the inside of the rock. And by the way, it's not just one kind of rock. You might be 7,000 or 8,000 feet down. There could be hundreds of different kinds of rock, each of which has its own chemistry, its own coefficient of friction, its own bonding chemistry with the cement. And you got one kind of cement that you want to bond to all those different kinds of rock. So it doesn't make any difference. That is disingenuous on the part of the industry to say, we're now using more steel and more casing to give you more protection. Totally irrelevant. Doesn't make a damn bit of difference. How do I know that the industry knows this? Because the industry publishes its own statistics. It has its own culture. It has its own journals. It has its own reviewers, its own editors. So I know how much on a Saturday morning you want to spend time looking at bar charts, but you're going to spend some time on bar charts. This one is from Schlumberger in their journal. They went out and they surveyed 45,000 offshore oil and gas wells and asked a very simple question. How many of them are leaking? Simple question, right? And they categorized all the data into a bar chart. So horizontal axis is how old the well was that they investigated, ranging from brand new wells to wells that were 30 years old. And the vertical axis is the percent of the wells that were affected by sustained casing pressure. In other words, there was gas coming up through one or more of the annuli outside the production casing. In other words, the well had failed. Structural integrity was not there. All right, this could be a graph of my age versus the number of pains that I have. And as you well know, even at birth, sometimes we hurt. But as we get older, we hurt more because more things go. Same thing, look, young wells fail at the rate of 1 in 20. Young wells, brand new wells, fail at the rate of 1 in 20. Remember that number, 5%. And as wells age, the failure rate goes up because that cement starts to degrade. There are ground motions that cause the cement to crack. The cement shrinks over time. The casing starts to corrode. The degradation between the casing and the cement goes to hell. The degradation between the cement and the rock goes to hell. And pretty soon, more than half of your wells are leaking. And how long are these Marcellus wells supposed to be in existence? Be careful how you answer this question. How long does every Marcellus well continue to have to exist in the state of Pennsylvania? Forever. Thank you. Forever on this graph. Okay, so a reasonable expectation is eventually all wells lose their integrity. All right, so I showed this once, and somebody from Halliburton said, "Ingraffea, you're full of you-know-what, because this is for offshore wells." This guy's from Halliburton. And I turned to him and I said, "You should know about offshore wells. And you should know about cement jobs in offshore wells. You should know about a cement job on an offshore well called the Macondo, where there was $1 billion investment in that well, and it failed because of a faulty cement job." So let's go onshore. So I dug this data. Again, this is industry data. This is the Society of Petroleum Engineering referee journal paper from 2009. These researchers went and surveyed 347,000 oil and gas wells in Canada. And again, they did the same thing. How many of them are leaking? And they find out that, somewhere around 4.5% of them. Older wells are leaking more than younger wells. You can see that here. So remember that, 4.5%, 5%. Earlier this week, I went to the Pennsylvania Department of Environmental Protection Compliance Database, which now is in pretty good shape. It took 4 years for them to get a reasonable, competent, professional database management system so that you, the public, can figure out what's actually going on. And I surveyed, and I asked how many violations were issued in 2011 to all the operators in Pennsylvania for loss of wellbore integrity. Let's go backwards first. Let's go to 2010. In 2010, there were 1,454 wells drilled in the Marcellus in Pennsylvania, and 90 of those wells were cited for wellbore integrity failure, migration of the type I just showed you. That's a 6.2% rate of failure. That number sound familiar? Industry says we're improving all the time. Now, we did tell you we were perfect when we got here, and we weren't. We admit it. We have to learn. My buddy Terry Engelder at Penn State says it's a really tough industry. They got to learn by actually experimenting in your backyards. So let's go to 2011. There are 1,937 wells drilled. There are 121 well failures. Exactly the same failure rate, to within 3 decimal places. Isn't that amazing? So let's see. I conclude that this data is consistent with previous industry data I showed you. In other words, this is a chronic problem the industry has always known about and has never been able to fix for obvious reasons. It's too damn complex to fix it. So what's rare? Rare is 6% early. Remember, these are wells that were drilled in the year in which the violation was issued. This isn't talking about what are those wells going to be doing 10 years from now, 20 years from now, 30 years from now. So the myth is fluid migration from faulty wells is a rare phenomenon. They'd like you to believe it only happens once in a million times, once in 1,000 times, once in 10,000 times, but there are going to be 100,000 wells in the Marcellus in Pennsylvania. That's what most experts say, in the Marcellus alone. So the truth is that fluid migration from faulty wells is a well-known chronic problem, and there's an expected rate of occurrence. If you're going to have 100,000 wells, you're going to have 6% of those wells, 60,000 wells, is that right? 6,000 wells, okay, are going to fail. How many people's well water contamination incidents is that going to cause? And what's the cost to the state? So health impact, there will be contamination. There has been, and there will continue to be, contamination of underground sources of drinking water with methane, perhaps drilling fluids, released hydrocarbons, and other things that are down there that are supposed to come up the inside of the well and come out the outside. So, truth, myth, you decide. I'm going to quickly go through this one and just point out a couple of things because I want to spend the rest of my time on the last myth, which is one of my favorites now. And since we already talked about local impact on individuals' groundwater, their water wells, I want to talk about the other end of the spectrum, which is global impact. There's lots of impact in between. So use of multi-well pads and cluster drilling, the industry says, well, that reduces the surface impact. They'll say, well, you know, we could go in and drill just one well on each pad and put a pad every 40 acres. But we're not going to do that. We're going to be nice to you. And we're just going to put a 7-acre pad every kilometer and drill 8, 9, or 10 wells from each one, and that's going to reduce the impact, which is a logical piece of nonsense because the comparison should be we don't drill at all or we do it our way because they would never drill a single well from a single pad for economic reasons. That's a stupid thing to do. So they're either not going to drill or they're going to drill it their way. That's your choice. That's the choice they're giving you, but they're telling you, in giving you that choice, which is no choice at all, they're being nice to you. All right, so I showed you this map before, Dallas-Fort Worth Airport. Here is a typical state-of-the-art drilling pad, 16 wells. All right, there is not a 16-well pad yet in Pennsylvania, but there's a permitted 9-well pad. And the number of wells per pad is gradually increasing as they're going back to places where they just put a pad and drilled a well to hold a lease. Now they're going back to drill more wells, which means the number of wells per pad will continue to go up. Here is, as of a year ago, the largest frac job on Earth. Just to give you an idea, this is 16 wells on one pad. Man-made lakes to supply water and volume for frac fluid return. 417 million gallons of water, 78,000 tons of sand, 8 million gallons of fracking chemicals, 10,000-foot laterals, and 40,000 horsepower for the fracking pumps. That's the fate of Pennsylvania because that's where the technology is taking them in terms of efficiency and economical development. So what does this look like? Translate the Dallas-Fort Worth Airport to Pennsylvania. So a spacing unit is an area that an operator deals with the landowners in that spacing unit, deals with DEP, gets a permit, and decides, for example, to put a pad here, orients that spacing unit ideally so that the laterals will intersect as many joints as possible. Remember the GO 101 thing? And drill as many wells as they want to, and that length can be whatever they want it to be, depending upon the technology, the geology, and the width is accordingly. So this might be something like a square mile, 2 square miles. And if we were to translate that into a land area in Pennsylvania or New York, it would look like that. Right? So ideally, again, this is the ideal situation where one operator would get permission from all the landowners in that area to deal only with that one operator. Then the idea would be to drill everywhere. And to drill everywhere, you'd have clustered pads. And on each pad, you would have multi-wells. Got it? Now, is this myth? Am I blowing smoke at this point? Okay, so let's take a look at what Shell, one company, has done with one county in our state, Pennsylvania. Here's a map of Tioga County. It's a map given to the EPA by Shell. They were bragging. They said, here's what we're going to do in Tioga County. I want to make sure you see what I see here. See that? You see it? What do you see here? Each one of those black dots is a proposed pad location. Each one of those regions, roughly rectangular, is a proposed spacing unit. Okay. Now, what is not on this map is the location of all the cities, all the towns, all the schools. In large measure, it really doesn't matter because they can always locate the pad, the regulatory distance away from a school or a downtown area, and still get the gas by the long laterals. Remember, that's one company's holdings. How many other companies are operating in Tioga County? Dozens. So all these areas that Shell doesn't have control over are being chopped up and leased out to the other companies. So in other words, the whole county is under attack. That's the way it's going to be. That's clustered pad, multi-well scenario in the real. Last time I spoke in Pennsylvania, somebody from the industry identified himself and he challenged me. He says, well, Professor Ingraffea, all this stuff that you're talking about clustered pads, it won't happen here because Pennsylvania actually has altitude changes. We have mountain ranges. We have valleys. You know, we can't put pads everywhere. Well, actually you do. And so I'm going to show you a couple of photographs. We talk about mountaintop removal for coal development. Why in the hell would a company decide to put a pad and drill for Marcellus gas in the Loyalsock State Forest of Pennsylvania on the top of a mountain? What's the answer to that question? No, because they can. I should have put a word ready here. It's called arrogance. They did it because they can. Why would they put a pad next door to a school, as they did in Dimmock? Because they can. It's arrogance. It's a way of showing power and control. Why would they build a mountain in order to build a pad? Because they can. Now, I don't think the guys in the audience that questioned me last time, Professor Ingraffea, we would never put a pad on a mountaintop. We would never put a pad on the side of a mountain. Hell, we'll just build a mountain. Why would they excavate that much earth and dump it into this valley where there's now a slope instability problem, by the way, which wiped out all of the dehumidifying equipment here? Why would they do that? Because they can. Because they can, because it's in keeping with putting a pad everywhere they can and drilling from each pad as many wells as they can to get as much gas as they can so they don't keep inventory in the warehouse. Okay, so there's my answer to we wouldn't put wells every place. Well, you are putting wells every place. And there will be, by the way, what percentage of the Marcellus Shale play has Pennsylvania experienced so far? How many Marcellus wells are in the ground right now? 5,000, and we're expecting 100,000? Okay. And I often get this comment, well, you know, we don't have a residual footprint. Tell the people living in that house that this is not much of a residual footprint. Yeah, so you have multi-well pads, you have multi-condensate tanks on the multi-well pad. So it's not something, I love this one. This is the excavation. By the way, look at the scale here. This is a truck. This is the excavation for a new compressor station out in Welling. 50,000 horsepower on that station. So this is not small-scale stuff. But again, I wanted to go quickly through this so I can get to the end. The myth is that multi-well pads, cluster drilling, reduce surface impact. Well, it doesn't.